Okay, so we start the next session, and we are very happy to have Lauren, and she will talk about hypersimplex and m equals to amplituhedron. Please.
So thank you very much for the introduction. It's lovely to be back with everyone, imagining that we're in the paradise that is KITP in Santa Barbara, while I'm sitting in the heat of Boston in my attic. Anyway, thank you for the invitation, and I'm going to speak primarily about joint work with Tomek Lukowski and Matteo Parisi. And this photo shows the sort of fishbowl room at KITP. If you feel like downloading my slides, they are available at the link above, and the two main papers that my talk is based on are shown here. So let me start by giving an overview of the objects in my talk. I will start by talking about the amplituhedron, which was introduced by Nima and Yara around 2013. And then I want to describe a much older object, the hypersimplex and the moment map, which was studied by Gelfand, Goreski, McPherson, and Serganova back in 1987. And the main theme of this talk is that these two objects, surprisingly, are related. And the way we discovered this connection was via this other object, which is the positive tropical crestmonian, which David Spire and I introduced in 2005. Okay, so I'll start by giving a bit of background on the crestmonian and amplituhedron, and then I'll tell you about positoroid triangulations of the amplituhedron, and then I will switch gears and talk about positoroid triangulations of the hypersimplex, and then I will explain how this T-duality map connects amplituhedron triangulations to hypersimplex triangulations. I'll give some results and conjectures, and then explain a little bit about how we discovered this coincidence. Okay, so the crestmonian, GRKN, is the space of k-dimensional subspaces in an n-dimensional real vector space, and I like to represent elements by full-rank k by n matrices. So the span of the k rows together gives our k-dimensional subspace. And then we can think of this crestmonian as matrices modulo the equivalence that two matrices, if they span the same subspace, we consider them to be the same. And now if I is a k-element subset of the numbers 1 through n, then the Pluker coordinate p sub I of A, here A is my matrix, this is the minor, is the determinant of the k by k submatrix of A, which is located in the column set I. And then the TNN, or totally non-negative crestmonian, is the subset of the real crestmonian where Pluker coordinates are simultaneously non-negative. And just some history, this definition was given by Postnikov in the early 2000s. Now, much earlier, Lustig had generalized the totally non-negative part of an arbitrary partial flag variety. And it's not obvious, but it turns out that his definition agrees with Postnikov's in the case of the crestmonian. Okay, so the crestmonian is, again, it's the subset. The TNN crestmonian is the subset where Pluker coordinates are non-negative. And we partition the TNN crestmonian into pieces based on which Pluker coordinates are strictly positive and which are 0. So now let's let script M be a collection of k-element subsets of the numbers 1 through n. And then we'll define SMTNN to be the subset of the totally non-negative crestmonian, where your Pluker coordinate p sub I is positive if and only if I lies in your collection. And Postnikov showed in his work from the early 2000s that this subset is non-empty. Well, if it's non-empty, then it's what he called a positoroid cell. And the word cell here means homeomorphic to an open ball. And he classified these cells and showed that they're in bijection with various combinatorial objects, including some kinds of permutations, and also some objects which you all know as on-shell diagrams, and he called Playbig graphs. Playbig stands for planar bipartite. Now, let me give a little bit of background and motivation for the amplituhedron. So this was, as I said, introduced by Nima and Yara in 2013. And this is, it's simply the image of the TNN Grassmannian under a quite simple map, actually. So let me give the precise definition. So this amplituhedron will now be indexed by 3 positive numbers, n, k, and m. So, and we want to make sure that k plus n is at most n. So let's let Z be an n by k plus m matrix such that its maximal minors are positive. So when you look at the k plus m by k plus m minors, their determinants are always positive. And now this induces a map from the TNN Grassmannian into a different Grassmannian of k-planes and k plus m space. And the way that map works is simply by matrix multiplication. So if you start with your k by n matrix A, representing a point in the TNN Grassmannian of k-planes and n space, then all we do is we multiply our k by n matrix by our n by k plus m matrix, and we get a k by k plus m matrix, which one can check has full rank, and hence represents a point in the Grassmannian of k-planes and k plus m space. And now the amplituhedron is just defined to be the image of the TNN Grassmannian under this map. So this is going to be a full dimensional subset of the Grassmannian of k-planes and k plus m space. Well, the physical motivation is that when n equals 4, its quote-unquote volume computes scattering amplitudes in n equals 4 super Yang mills. Okay, so in this top block, I'm just reminding you of the notation of the amplituhedron. And I'll just mention a few special cases. So the m equals 4 amplituhedron is the one that most of you will care about. It encodes the geometry of tree level scattering amplitudes and planar n equals 4 super Yang mills. In fact, the m equals 2 amplituhedron, which I'll talk about today, is extremely interesting. Well, it's a toy model for the n equals 4 case, but it also has some physics motivations as well. It governs the geometry of scattering amplitudes in n equals 4 super Yang mills. It's sub-leading order in perturbation theory for the MHB sector. And it's also relevant to the next MHB sector, giving more of a connection with the geometry of loop amplitudes. Okay, so m equals 2 is what we will primarily care about. In order to understand the volume of the amplituhedron, a important technique is to find triangulations of the amplituhedron. So what do we mean by that? Well, this amplituhedron, ANKM, this has dimension k times m, which is in general less than the dimension of the TNN Grassmannian, which is the domain of our map. And so our map Z tilde, defining the amplituhedron, is generally not injective. But let's recall that we have this decomposition of the TNN Grassmannian into positoroid cells. And so a very natural question is to find a collection of km dimensional cells of the TNN Grassmannian where the Z tilde map is injective, such that the images of cells are disjoint and they cover a dense subset of the amplituhedron. So we're basically trying to find pieces, cells in the TNN Grassmannian GRKN which have the right dimension and map injectively to the amplituhedron such that they cover it. Okay. As a mathematician, I have some problems with calling this thing a triangulation, but it's been used enough in this context that I need to stick with this word triangulation. And one significance of these triangulations is that the BCFW recurrence can, anyway, conjecturally, be formulated as giving triangulations of the m equals 4 amplituhedron. Okay, so this is just again, a review of the notion of triangulation. And now, just because it's so fun, I can't resist, I want to mention this conjecture of Stephen, Karp, and Yang and myself, which I think I mentioned at KITP 3 years ago, and anyway, it's still wide open. So what does the conjecture say? It says that if m is even, then the number of cells in a triangulation of the amplituhedron is this number, m of k, n minus k minus m, comma m over 2, where, what's this number, capital M? Well, it's given by this beautiful product formula. And I'll just say a tiny bit about that. Let me just say the conjecture is completely wild in that we do not have conjectural triangulations of the amplituhedron, which have this size. But the conjecture is consistent with results and conjectures that are believed for m equals 2, m equals 4, and k equals 1. So anyway, so the conjecture fits everything that we know to be true so far. And this is a very striking number in combinatorics. It counts the number of plane partitions contained in an A by B by C box. There's a picture up there. It also counts collections of C non-crossing lattice paths in an A by B rectangle. It also counts rhombic tilings, perfect matchings, K-Coulé structures. So it's a very nice combinatorial number, and it's sort of striking that it seems to describe triangulations in the amplituhedron. But anyway, so again, m equals 2 is our main focus here, and the conjecture says for m equals 2, there should be n minus 2 choose k cells in a triangulation of this amplituhedron. Okay, so now I want to shift gears and talk about the hypersimplex. So what is the hypersimplex? It's a very, very simple polytope. So let's let E1 through En be the standard basis of Rn. And if I is a subset of 1 through n, I'll just let E sub I be the sum of all the E sub little i's coming from my subset. And now the hypersimplex, delta Kn, is the convex hull of E sub I, where the size of I is k. So it's just the convex hull of all of the 0, 1 vectors in Rn, which have precisely k 1s. The picture on the screen shows delta 2, 4. Equivalently, this is the intersection of the unit cube with this hyperplane where the sum of the coordinates is k. And it's not hard to see that this polytope is a polytope of dimension n minus 1. And our example here is delta 2, 4. And I don't know if you can see my earrings in Zoom, but they show delta 2, 4. Okay, so now I want to talk about a map that relates the crestmonian to the hypersimplex. Okay, so this is just a review of the definition of hypersimplex. And now there's this old map called the moment map from the crestmonian, defined as follows. So if A is my element of the Kn crestmonian, or in other words, I can think of it as a K by N whole rank matrix, then I define mu of A to be a vector in Rn, and it's defined as follows. So first of all, the denominator is just a scalar that's the sum of the squares of the Plucker coordinates, so that's just some simple scalar. And the numerator, all I'm doing is I'm adding up the indicator vectors E sub I, where I is a k element subset of 1 through n, and I'm just scaling, I'm just using a coefficient that's proportional to the size of that Plucker coordinate. So this maps our crestmonian into Rn. And the image of the full crestmonian, which is also the same as the image of the TNN crestmonian, is exactly delta Kn. And if I start with any positroid cell, then the image of my cell is a polytope, which is called a positroid polytope. And I think I mentioned very briefly that the positroid cells of the crestmonian are indexed by decorated permutations, or if you like, affine permutations. And so I'm indexing both the cells and the polytopes by that permutation pi. Okay, and now, following the definition we made of triangulation of amplituhedron, we're going to define a positoroid triangulation of the hypersimplex to be a collection of n-1 dimensional cells of the TNN crestmonian where the moment map is injective. So remember, the hypersimplex has dimension n-1, and so I'm basically looking for a collection of positoroid cells of the TNN crestmonian that have the biggest possible dimension such that the moment map can be injective. And additionally, I require their images to be disjoint and to cover the hypersimplex. Okay, to be precise, I'm requiring that the images of the interiors of these polytopes are disjoint, and together the polytopes cover the hypersimplex. So this is just a straightforward analog of the definition of triangulation we made before for amplituhedron, but now making it for the moment map. Okay, so now I want to make this very weird and unexpected claim, which is that the triangulations of the hypersimplex, delta k plus 1 comma n, and the amplituhedron, a n k2, are closely related. And let me just explain why this claim is weird. It's weird because the dimensions of the two geometric objects are different. The dimension of the hypersimplex is n-1, while the dimension of the amplituhedron is 2k. The hypersimplex is a polytope, but the amplituhedron is not. The hypersimplex is related to grk plus 1 comma n, while this amplituhedron is related to a different crestmonian. And the moment map just doesn't look like the amplituhedron map. At least I don't see any similarities. But nevertheless, we're going to claim that triangulations of the hypersimplex and the amplituhedron are very, very related. Okay, so just to recap, we have our two notions of positoroid triangulation. Our amplituhedron map is basically matrix multiplication, whereas our moment map from a different TNN crestmonian is defined by kind of scaling, taking linear combinations of the indicator vectors based on the magnitudes of the supercoordinates. So positoroid triangulation for the amplituhedron is a collection of 2k dimensional positoroid cells where z tilde is injective, such that images are disjoint and cover the amplituhedron. And a positoroid triangulation of the hypersimplex is a collection of n-1 dimensional positoroid cells where mu is injective, such that images are disjoint and cover the hypersimplex. Okay. All right, so how could these triangulations be related? So, of course, the triangulations of the amplituhedron are 2k dimensional cells, while triangulations of the hypersimplex are n-1 dimensional cells. But nevertheless, we can compare the number of cells that we expect to comprise a triangulation. And according to this wild conjecture with Karp and Zhang, there are n-2 choose k cells in any triangulation of the amplituhedron, for m equals 2. And then, according to a recent result with David Spire, positoroid triangulations of the hypersimplex also use precisely n-2 choose k cells. And so one would like to concretely connect these two kinds of triangulations. Okay, so we make this map that we call a T-duality map on positoroid cells. But before describing the map, I need to first say just a little bit more about the permutations indexing positoroid cells. So a decorated permutation is a permutation in which every fixed point is, we'll just call it either a loop or a co-loop. So every fixed point has one of two colors. And according to the work of Postnikov, the cells S pi of the TNN crestmonian are labeled naturally by decorated permutations pi on 1 through n with k anti-exceedances, where an anti-exceedance is a position I, or pi of I is less than I, or pi of I is a fixed point, which is a co-loop. Okay, so triangulations of the amplituhedron consists of two k-dimensional cells of GRKN, while triangulations of the hypersimplex consist of n minus 1 dimensional cells of GRK plus 1 comma n. So we have to map our n minus 1 dimensional cells of GRK plus 1 comma n to two k-dimensional cells of GRKN. Okay, so now we just define this very simple map. So if you give me a loopless decorated permutation pi, which I'll just write as a list of numbers a sub 1 through a sub n, and this means 1 goes to a sub 1, 2 goes to a sub 2, and so on, then we'll define pi hat to just be the same permutation after kind of cyclically rotating the coordinates. And we'll declare that in pi hat, fixed points are loops. So we call this the T-duality map. And I should say that the generalization of this map to m equals 4 already appeared in earlier works and was observed as a duality between formulations of scattering amplitudes for n equals 4 in momentum space and in momentum twistor space. So this is kind of an m equals 2 version of that map. Okay, so now here's our main conjecture on T-duality. So let's start with our loopless decorated permutation pi, and pi hat is as above. Then a very simple lemma is that the T-duality map gives a bijection between the loopless cells of the TNN crestmonian of k plus 1 comma n and the co-loopless cells of GRK comma n. And moreover, this map does the right thing on the dimension of the corresponding cell. So it just gives a sort of, it takes the dimension of your cell on the left-hand side, and the cell on the right-hand side will have dimension which is the same as before plus 2k minus n minus 1. So in particular, it will map cells of dimension n minus 1 to cells of dimension 2k. So it's doing the right thing on dimensions of cells. And then our main conjecture is that a collection S pi of cells in the TNN crestmonian of k plus 1 comma n gives a triangulation of the hypersimplex if and only if the corresponding collection of cells in the TNN crestmonian of k planes in n space gives a triangulation of the m equals 2 amplituhedron. So there seems to be a very, very precise connection between triangulations of this very simple classical object, the hypersimplex, and triangulations of this much newer object, the m equals 2 amplituhedron. Okay, so we have rather compelling evidence for this conjecture. So I'll say a few words about that. I want to talk about what have been called generalized triangles. So we'll say that S pi is a generalized triangle for the hypersimplex if the dimension of this cell is n minus 1 and the moment map is injective on it. So these generalized triangles are the cells that you want to use in your triangulations. And analogously, we'll let S pi hat, we'll call it a generalized triangle for the amplituhedron if its dimension is full dimensional, 2k, and the amplituhedron map is injective on it. So it's not hard to show using kind of classical results about moment map that the generalized triangles for the hypersimplex correspond to on-shell graphs, which are trees. Now, on the other hand, the generalized triangles for the m equals 2 amplituhedron have been studied in previous work of Lukowski, Parisi, Spradlin, and Volovich, and they correspond exactly to collections of non-intersecting polygons in an n-gon. And T-duality, which sends our permutation pi to pi hat, if you look at the combinatorial objects associated to them, they precisely, T-duality maps generalized triangles to generalized triangles, and on the level of combinatorics, it relates the non-intersecting polygons studied by Lukowski, Parisi, Spradlin, and Volovich to dual trees. So this picture at the bottom left is a non-intersecting polygon. It's a collection of non-crossing polygons inside a bigger polygon. And you choose some triangulation of it, of our red polygons. And there's a very simple way to associate a dual on-shell graph to that non-intersecting polygon. And this is precisely what T-duality does. This is exactly how T-duality maps generalized triangles to generalized triangles. Okay. Another piece of compelling evidence for this main conjecture is that you can look at recursions giving triangulations of both the hypersimplex and the amplituhedron. So, so there's a very simple recursion in terms of on-shell diagrams giving many triangulations of the hypersimplex. And so that recursion is shown in pictorial form here. And on the other hand, there's also a recursion giving many triangulations of the m equals 2 amplituhedron. And this was proved to give triangulations by Bao and He. And what we show is that the recurrences are exactly in bijection via T-duality. Anyway, so T-duality maps many triangulations of the amplituhedron to many triangulations of the hypersimplex. But I do want to point out that not all triangulations are obtained via these recurrences. Okay. So in my last few minutes, I just want to explain why we discovered this link between the m equals 2 amplituhedron and the hypersimplex. Because on the surface, it looks like it's like I would have never thought to try to relate these objects. But it was a kind of numerological coincidence that made us realize something was going on. So we were looking at good triangulations of the amplituhedron, so those where boundaries of generalized triangles intersect nicely. And looking at numerology of these good triangulations, you know, looking at how many there are and so on, it recovered some numerology of the positive tropical crestmonian. And so we were trying to figure out how is the m equals 2 amplituhedron connected to the positive tropical crestmonian. So the first step was to relate the positive tropical crestmonian to some kind of triangulations. And the right thing to do there is to show it controls triangulations of the hypersimplex. And so then we guessed that triangulations of the amplituhedron must be related to triangulations of the hypersimplex. Okay, so we'll just say a little bit, I'll just explain that in a tiny bit more detail. So many of the known triangulations of the amplituhedron are bad in the sense that boundaries of images of cells overlap badly. But we'll say that a triangulation is good if whenever, this is in the amplituhedron now, we'll say a triangulation of the amplituhedron is good if whenever you look at the images of two cells, and if you look at where they intersect, if it has codimension 1, you require that intersection to equal the image of another cell, S pi, that's in the closure of the two you started with. Okay, and now if you start counting these things, then the number of good triangulations of the amplituhedron for k equals 1 is the Kavli number. And if you look at the number of good triangulations of the amplituhedron for k equals 2, you get the sequence 1, 5, 48, 693. And these are numbers that David Spire and I computed a long time ago when we were studying the positive tropical crestmonian. So that object is a polyhedral fan such that the number of maximal cones for trop gr2n is the Kavli number, and the number of maximal cones in trop gr3n is exactly the sequence 1, 5, 48, 693. So we needed to explain this link between the amplituhedron and the positive tropical crestmonian. And to do so, the first step was to show how the positive tropical crestmonian was connected to some kind of triangulations. Okay, so so before I say more about the positive tropical crestmonian, I'll just mention that it's appeared in a flurry of physicsy papers in the last year. I'm sure I have omitted some references here because I haven't even gotten into 2020. But anyway, this is a smattering of them. And so let me now define the positive tropical crestmonian. In our original paper, we defined it as the positive part of a tropical variety defined over Priseau series, and showed this could be computed as a common refinement of some fans, or equivalently as the dual phantom in Minkowski sum of some Newton polytopes. Anyway, you can look at our paper or the appendix of these slides for the definition, but I'll just for now just give you a much simpler way to describe it. So this positive tropical crestmonian is just a subset of R to the n choose k that has a fan structure. So we'll say that a vector P, so P is in R to the n choose k, so its coordinates will be k element subsets of 1 through n. So let's say this vector P is a positive tropical Pluker vector if for any A, B, C, and D, and S, a k minus 2 element subset disjoint from A, B, C, and D, we have one of these two inequalities. And these two inequalities should remind you of the three-term Pluker relations. So anyway, so we say a vector P is a positive tropical Pluker vector if it satisfies this kind of tropicalized version of the three-term Pluker relations. And then it's a recent theorem that we proved together with Spire and was independently proved by Arkhani Hamid, Lamb, and Stratton, that the positive tropical crestmonian is exactly the set of positive tropical Pluker vectors. Okay, so anyway, so you can just think of this as the definition of the positive tropical crestmonian. And now let's connect it to triangulations. So, so the inspiration for this was an old paper of Spire, which in turn built on work of Kapranov, and this old work related tropical Pluker vectors to nice matroid subdivisions of hypersimplex. And so we just needed a positive analog of that. Okay, so so to construct nice triangulations of the hypersimplex, which in mathematical terms are called regular subdivisions, we choose vectors in R to the n choose k, and we think of our vector R to the n choose k as a height function, as giving a height function on our vertices of the hypersimplex. So remember, the hypersimplex has n choose k vertices, and what I'm going to do, so my hypersimplex is sitting in R to the n, and what I will imagine doing is over every vertex e sub I of the hypersimplex, I'm going to lift it up. I'm going to embed my polytope into a one-dimensional bigger space by lifting up each vertex to a height, which is a real number, which is p sub I. So this is giving me a bigger polytope now in R to the n plus 1. But now if you project this back down to the hypersimplex by looking at the lower faces of this bigger polytope, this gives a regular subdivision. So this gives a nice decomposition of the hypersimplex into polytopal pieces. And so what we showed was that if P is a vector in R to the n choose k, then the following statements are equivalent. So the first statement is that P is a positive tropical Pluker vector. And the second statement is that every face of D sub P is a positoid polytope. Or in other words, we have found a decomposition of the hypersimplex into positoid polytopes. Okay. Yes, as I mentioned, this is a positive analog of older results and was also anticipated or known by others, but hadn't been written down ahead of time. Okay, so what is the upshot? The upshot is we now have a way of relating the positive tropical crestmonian to some kind of triangulations, and in particular to triangulations of the hypersimplex. Okay, so now, so there's many triangulations of the m equals 2 amplituhedron. Some of them are bad in the sense that boundaries interact badly, but some of them are good, and the ones that are coming from the positive tropical crestmonian behave well at the boundary. So these are what we would call good. Let's see, maybe I'll just, so I'm not going to say very much about it, but I'll just say that one thing that we do in our paper with Tomek and Mateo is to introduce this object called momentum amplituhedron, which is a generalization for even m of the object m sub mk4, which was previously defined by Damgaard, Ferro, Lukowski, and Parisi. And this momentum amplituhedron should be the object that gives an analogous story to what I've talked about today, but for any even m. So in particular, this momentum amplituhedron, when m equals 2, should be sort of morally the same as the hypersimplex. And for m equals 4, this was previously studied, and we have a definition that works for even m. Okay, so this is just a kind of a summary of what I've explained today. So we have two maps. We have the moment map from a crestmonian of k+1 planes in n space to a polytope called the hypersimplex, which is a classical and well-studied object. And on the other hand, we have the amplituhedron map from a related crestmonian of k planes in n space to the m equals 2 amplituhedron. And there are triangulations of both of these objects, which consist of n-2 choose k cells. And T-duality seems to be the link between these two constructions. It seems to precisely map triangulations of the hypersimplex to triangulations of the amplituhedron. So let me just mention a few questions. It would be really nice to understand why the moment map is related to the amplituhedron map. I mean, we have some compelling evidence that they are related, but I don't feel like we have a good understanding of why they're related. It would be really nice to use this relation to better understand the amplituhedron, given that the hypersimplex is very well understood from certain points of view. In the old work with David, we found a connection of the positive tropical crestmonian to cluster algebras, and it would be very nice to make a direct link of cluster algebras to the amplituhedron. So I will stop there, and thank you very much.
Thank you very much. And I actually have two questions. The one is about this wild conjecture about counting, this formula. So for m equals 4, it agrees with the Narayana number for the number of BCFW stuff.
Yes.
And so is it possible to rewrite this in some more like binomial form, or when we higher m amplituhedra corresponds to some like funny patterns of factorization, not into 2 but into 3, it still seems kind of combinatorial in this sense.
Yeah, there are different ways of writing this formula. I guess I don't know exactly how you want, what shape of formula you want, but there are other ways to rewrite it.
Well, for m equals 4, it corresponds to factorizations, the number of BCF from the physics point of view, factorizing the higher point thing into lower point thing. For even m, higher m, there should be some new pattern of factorization, not into 2, but into 3. So I guess, so my guess would be that the counting would kind of reflect that.
I see. So you're saying for m equals 2, for m equals 2, it's 1 binomial coefficient. For m equals 4, it's like 2 binomial coefficients. And you're asking for higher, even M, how could we make it look similar?
Yeah. Right.
Oh yeah, that's a very good question. I don't know offhand, but I'll think about that. Yeah, that would be nice.
And then for this, so we have also these triangulations we call local triangulations, which I guess mathematicians don't like so much because they don't call them triangulations.
I think I must have missed this. What is local triangulation?
Well, the local triangulation is that you use external points to triangulate. So you don't introduce any, like in the polygon case, you don't introduce any new lines. You just kind of intersect the lines which are already there, and that introduces a point outside, and that you use to triangulate. Because at the level of form, it doesn't introduce any new spurious boundaries. So for that reason, we call them local. Yeah, I was just wondering if that makes any sense for this delta.
I guess I need to look at your definition a little more closely.
It will be a triangulation with a dual polytope. So
dual polytope, yes. Yeah.
Is there any kind of picture for subdivisions or counting triangulations of the dual of the hypersimplex, which is not
right. That's a good question.
Yeah. So that these things that he's talking about in the case of polytopes are just triangulations of the dual. So that's a sort of a natural question.
Yeah.
Okay.
True, that would be just for k equals 1, right? So for higher k,
No, but the point is that the hypersimplex is always a polytope. So that's sort of that is a nice question. Is there anything known about? Well, I guess that part of the problem is it's not obvious what to mean by the positroidal subdivisions once you take the dual. So, but I suppose you could just ask about all possible triangulations of the hypersimplex. I don't know.
Right. What's the paper where you introduce these local, or look at these local subdivisions?
That's even with the paper with Andrew Hodges from 2010.
Okay.
About just polygons. Yeah.
I see. Okay.
Lauren, can I ask a simple question? So you have a triangulation of the you have subdivisions of the hypersimplex, so you're sort of covering the hypersimplex with cells of dk plus 1n under the moment map, and then they descend under your T-duality map to triangulations of the amplituhedron, right?
Right.
We would say exactly the same words for n equals 4, where we would take a triangulation of the momentum amplituhedron in terms of 2n minus 4-dimensional cells of momentum amplituhedron, and they should descend to triangulations with 4k dimensional cells of the momentum twister amplituhedron.
Right.
Is there some sense in which the momentum amplituhedron for m equals 2 is just the hypersimplex somehow, or not? I mean that seems like an obvious place to try to make the connection, because they're not, you're using the T-duality map to connect them, and we already have something that connects them. You know, there should be some sort of a momentum space version of the amplituhedron even for n equals 2. And then at the very least, either it is the hypersimplex, or those two should be even more closely related to each other.
Right. So you're asking how closely related is the hypersimplex to the m equals 2 momentum amplituhedron?
That's right. I don't know if our friends actually defined the m equals 2 momentum amplituhedron. I can't remember if they defined one.
So I think their first paper was for m equals 4, and then in the end of our paper we do it for any even m.
Oh, I see. You give a definition for any even m. Okay, good.
Right.
So is the m equals 2 momentum amplituhedron in any obvious way related to the hypersimplex, or are those still mysteriously connected to each other?
Yeah, that's a very natural question. I haven't looked at that too much, but I know that I think Tomek and Livia and maybe someone else have a paper on the boundaries of the momentum amplituhedron, so maybe they could say more. I don't know if one of them wants to answer.
Livia? Tomek? Maybe not, but Lance had a question as well, so maybe we'll get back to it later.
I just have a very simple remedial type question. I mean, T-duality, as far as I know, is a Z2 operation. You do it a second time and you go back. But you showed this pi hat, which involves cycling by something of order n. That doesn't look like Z2, so what am I missing?
Well, yeah, so so this is not going to be an involution.
Yeah, involution, that's the word I wanted. Yeah.
Right, it's not going to be an involution. We did have some discussion about whether it's appropriate to call this T-duality or not.
Du, too.
What?
Duality kind of means
Right.
involution almost.
Right, well, anyway, so I
But
didn't
then what happens if you do it again? What does it do if it doesn't come back?
Yeah, so the thing is, so first of all, it only makes sense if you are starting from a cell of your crestmonian, which is loopless, and then it maps you to a crestmonian where your K index has gone down by 1. So if you try to do it a second time, it may not be well defined, but if it is well defined, it'll still decrease your K index on your crestmonian.
Can I answer this question partially in more familiar physics language, maybe? So
sure.
This is the whole. This is just for m equals 4. This is the usual amplitude Wilson loop duality, and it's reasonable to call it T-duality because in the context of string theory, we think about it as a fermionic T-duality. So you go back and forth between Wilson loops and amplitudes. But as you know, when we go from an amplitude to a Wilson loop, we strip off the MHV factor, including the momentum conserving delta function. So they're not entirely on an equal footing when you do that. Now, from the very early days of the story of the positive Riemannian, we understood that that connection, and more generally the whole Yangian, but minimally that connection was a very simple property of the Riemannian geometry. And indeed, it took you from GKN, and it mapped cells in GKN to GK minus 2n. Okay, and you could keep going to go to GK minus 4, and you could just keep on going as much as you want. And you could start in the original twistor space and go to momentum twistor space and yet another twistor space, other momentum twistor space, and there are all these connections. All these guys are there, but generically, you won't end up having things that have. You won't end up on cells that give you non-zero answers for generic external data. So that we're familiar with that back in the original twistor space, where amplitudes have support on on singular low-dimensional curves and not for generic twistor data. So what's special about using momentum space or momentum twistor space and the cells of the correct dimensionality is that we get smooth objects. But you could indeed keep dualizing all you want and then get funny objects and funny further duals of the spaces, which have strange kinematic support. They all mean something. They're all Yangian invariant formally. But anyway, so that's the funny business that it doesn't square to 1 because you're going from because you're stripping off this MHV factor when you go from one to the other. That was sort of clear from physics. What these guys have done is show the generalization of that for any m, for any even m, I guess, right? Is that right, Lauren?
Yeah, that's right.
Yeah. So for any even m, there's a map of this sort that that we can, I think of as sort of different ways of making different conformal generators inside the full SLM/M Yangian manifest. And the sort of maps between those different representations where one superconformal symmetry is obvious and the other ones are hidden that map is carried out by what they call the T-duality map more generally.
So Tomek,
are you saying one action of this map coincides with one direction of T-duality?
Exactly. That's right.
They're not the same thing. And
that's right. Yeah. So I mean,
T-duality, I mean, in principle, it is invertible. It exchanges a tau and sigma on the string world sheet, and
that's right. Yeah.
Be some kind of a super Wilson loop that allows you.
Yeah. So the fermionic T-duality is a little funny. I mean, again, also ordinarily T-duality just maps a theory to itself. Here you map an amplitude to a Wilson loop, so it's not quite, the objects on the two sides are not exactly.
Well, that's because you're living down on the field theory version of it. In the full string theory, it probably doesn't really do exactly that, does it?
I think for the observables that are, I mean, if you start with
I mean, one is a description of small string scattering. The other is a description of stretched string scattering.
yeah, I guess
And they're supposed to be equivalent, but
yeah. I don't know if there's a complete description of what the general string scattering amplitude, rather than just the like gluon part, would be in terms of the dual Wilson line. So I don't know how to answer. I don't know how to think about that question. Probably maybe other people do, but I don't have an understanding.
So Tomek wanted to comment
yeah, sorry.
the previous question.
Can you hear me?
Yes. Yes.
Okay. Yes. Yeah, Nima's question was about what is the relation between momentum amplitude for m equal to 2 and the hypersimplex directly, right?
Yes.
So I think that there are different objects because one is really a polytope. So you can think about this as, I mean, you can think about this as taking it to a single projective space and just a projective polytope. The other one, so momentum amplitude for m equal to 2 lives in a product of two projective spaces, and it's a curvy object.
Mm-hmm.
And the thing which they have in common is the fact that the boundaries are the same. So they have the same combinatorial structure of boundaries, but as geometric shapes, I think that they are different.
But is it easier to understand? Is it even easier to understand how the hypersimplex decomposition is related to the amplituhedron, for the momentum amplituhedron for m
It's the
equals
same.
2?
You take exactly the same cells in the crestmonian, in a positive crestmonian.
Sure. But I'm saying, is it? I'm just asking: is the connection to the real connection to the m equals 2 amplituhedron just descending from the momentum amplituhedron for m equals 2? Is the connection with the hypersimplex most obvious in momentum space? That's what I'm asking.
I'm not sure if I understand the question.
Maybe I'll ask it another way. We know that for m equals 4, we know that the boundaries of the momentum amplituhedron are not identical to the boundaries of the ordinary amplituhedron, right?
That's correct.
So are the boundaries of the momentum amplituhedron for m equals 2 kind of the same as the whatever it could mean, the same as the boundaries of the hypersimplex, or not?
Yes. So the structure is exactly the same. So hypersimplex has two types of boundaries, where one is of the type delta k n minus 1, and the other is of delta k minus 1 n minus 1, and the same is true for the momentum amplituhedron.
Okay. But then what about the m equals 2 amplituhedron downstairs? Is it missing boundaries like we expect for m equals 4? I see. So it's still missing boundaries. So good. So the connection between the boundary structure is just identical at the level of the momentum amplituhedron for m equals 2.
That's correct. But the relation between triangulations is in all three objects.
Okay, great.
But if you take a triangle, if you just look at a single triangle in the amplituhedron, it's a very strange object. I mean, if you take the simplest possible one, like for 5 points, the one which we usually call 1, 3, 4, for k equal to 2, it has a very strange structure of boundaries. But if you move directly to the momentum amplituhedron, this is a very simple object. So the triangle has a nice structure of boundaries, but not in the amplituhedron space.
Thank you.
Okay, thank you. So thanks, Lauren, again. Nice talk.